First of all, many thanks for the invitation to the colloquium. It's a great pleasure for me to be here in St. Petersburg. So actually, my intention was to give you some feeling about the interplay between the Martingale methods, some classical questions of Fourier, of harmonic analysis, so about Fourier multipliers, and related objects. Okay, so let us start with the motivation. All right, so the Berling-Alfors operator will be, well, very important for us today. Okay, so Berling-Alfors operator, sometimes it is called the complex Hilbert transform. It's given by the following formula. Okay, so here this integral must be understood in the sense of Cauchy principal values. Okay, because well, there is some singularity in the denominator. All right, so this is the Berling-Alfors operator. Or complex Hilbert transform. Okay, I will say a few words about it in a moment. All right, and well, Berling-Alfors operator is an important object. It's a very convenient tool in various problems of partial differential equations, some quasi-regular mappings. Okay, and it's often important to have some good bounds for this operator. All right, and in particular, one may ask about the LP norm of such an operator. Okay, well, it falls into the scope of Calderon-Zygmunt singular integral, so it's bounded in LP for P strictly between 1 and infinity. But there is a question about the precise norm. All right, and there is a celebrated conjecture by Ivanets, who claimed that this norm is P star minus 1, all right, where this P star is the maximum of P and its harmonic conjugate. Okay, so P over P minus 1. Okay, wherever Q happens, it's always the harmonic conjugate to P. All right, so this constant P star minus 1, this conjectured LP norm of the Berling-Alfors operator is, well, given by these two formulas depending on whether P is smaller or 2 or larger than 2. Okay, so this is a celebrated conjecture. It's from 70s. Okay, and it's still open. Okay, that's the first question. Okay. All right, the Berling-Alfors operator has plenty of interesting properties. So, in particular, it's a Fourier multiplier. Okay, so the Fourier transform of BF is just the Fourier transform of F multiplied by the following expression. Okay, the xi bar over xi. Okay, Fourier multiplier with such a symbol, xi bar over xi. Okay, furthermore, another remarkable property of Berling-Alfors operator is that it switches the complex derivative, okay, one into another. Okay, so there is also the important property. Okay, so that's just restatement of Ivanets' conjecture. All right, so we see directly from this property, okay, we see that this conjecture of Ivanets can be restated in this form. Okay, perhaps I will only mention one fact, namely, it is known, there are some examples which show that this constant, that this norm, this LP norm, is at least P star minus 1. Okay, all right. Okay, there's another important inequality which plays a role in the theory of quasi-regular mappings. It's the so-called Aria distortion theorem. All right, and it's the following. Okay, there are several authors given here. So perhaps let us start with explanation of this inequality. So you see what you take the unit disk of the complex plane. Okay, you take some subset of this unit disk, okay, and you integrate, okay, this Berling-Alfors operator acting on the indicator function of E, okay, integrate it over D, okay, and then it turns out that there is a universal constant C with this, well, universal, actually it's pi over 2, okay, such that this inequality holds, okay, and these bars here are just the Lebesgue measure. All right. Well, actually, this this statement, this inequality, was proved first by Gering and Reich in '66. Well, in a weaker form, actually. There was a constant here in front of E, some constant. Then there were some papers which, well, decreased this constant here, and finally Astala proved in '94 that this constant here can be removed. It's just constant 1. Okay, and he proved this with some constant C, and then Eremenko and Hamilton in 1995, they proved that this C actually, the best C one can take here is pi over 2. All right, so this inequality is important for some applications. Okay, so, well, there are other related problems which can be treated. Of course, well, we had this LP bound. One can study some weak type bounds, logarithmic bounds, restricted bounds, and other problems of this type. There are, as I mentioned, there are many applications, some elliptic equations, quasi-conformal mappings, and so on. So these things are important. And, well, of course, one can ask similar questions about other Fourier multipliers. Okay, so the Berling-Alfors transform is just an example of a Fourier multiplier. There's a natural question: what can be said in the general setting? All right. So this is just the motivation, and, well, so now the outline of the talk. So my intention that the main part of the talk will deal with the martingale study of these problems. Okay, so we'll see how to what are the probabilistic versions of these previous results, okay, of this Ibanez conjecture, of this Gering-Reich inequality. We'll see how to treat these problems with martingales, okay, using probabilistic methods. Okay, then we'll show how to deduce, how to obtain these desired estimates using martingales. Okay, we'll also see how to deduce the results for Fourier multipliers, and, well, if time permits, okay, I will say a few words about sharpness, about how one can construct extremizers which give optimality of the constant, or asymptotic optimality of the constant. All right, and it turns out that there some beautiful objects appear, laminates. There are special probability measures on matrices. Okay. All right, so we start with martingale study. All right, so okay, so let us start with definition. So, well, let us recall that the martingale is a sequence of random variables. All right, on some probability space omega fp. Okay, it is adapted to the filtration. Okay, so we have an increasing sequence of sigma algebras of f. Okay, this f0, f1, f2, and so on, so on. Just the increasing sequence of subalgebras. Okay, and the martingale condition is the following, right? That the conditional expectation of the next variable with respect to the current sigma field, okay, is just the current variable. That's the martingale property. Okay, and these objects will be important for us. All right. Okay, so with any martingale, we can associate the corresponding difference sequence, okay, by this difference sequence dfk. So actually, it's the definition of this difference sequence is given here. Okay, so for each n, we want this equality to hold. So alternatively, you know, this difference is given here. Okay, and df0 is equal to f0. All right. Okay, as an easy example, so if you take, well, any function, say from L1 or whatever, okay, and you expand it into the Haar series, all right, and you take a look at the sequence of partial sums, okay, look at such a sequence, all right, and this is a martingale adapted to the natural filtration, the dyadic filtration generated by the Haar system. Okay, this will be also important to us. Okay, another very important notion is the so-called Martingale transform. So what you do, take a look first at this definition, okay, of the difference sequence. Now what you can do, you can try to multiply, to transform these differences, okay, then actually you do this here, all right. So we multiply these differences by vk, where we assume that vk is a fk minus 1 measurable random variable. Okay, in such a situation we call that this is predictable. Okay, if such a measurability holds. Okay, so this is just predictability. Okay, so this guarantees, this predictability guarantees that this transformed sequence is also a martingale. Okay, it's easy to check that this condition with G here is also satisfied. Okay, for some technical reasons we assume that this V case, okay, are bounded by 1. Okay, there is a very special case of this transform, the so-called plus minus 1 transform, and it corresponds to the case when, for this V case, we take deterministic sequence of signs. So either plus 1 or minus 1 and deterministic, so no randomness here. Okay, so in such a special transform will be called plus minus 1 transform. Okay. So classical result of Burkholder, which can be when viewed as a step towards Ibanez conjecture, okay, it's the boundedness of the martingale transforms. Okay, so it's so Burkholder said that for fg as previously, okay, so this is martingale, this is transformed by a certain predictable sequence bounded by 1. There is an absolute constant Cp such that we have this bound, okay, and this inequality holds for peaks strictly between 1 and infinity. This is the classical celebrated result of Burkholder from 1966. All right, in the particular case, okay, if we use as this Fn and Gn, we use this Haar series we talked previously. All right, we reprove in this way another very classical result of Paley from 1932, which says that, well, these partial sums, okay, corresponding to the Haar system, okay, and here we have this transformed sums by some sequence of signs, okay. So this is just the particular case of this result on martingales, okay. So in particular we get this inequality for the Haar system, okay. And finally, final thing on this slide is that, well, there is a problem. What is the best constant here? This Cp. Okay. There is a well, very nice question, and this question was answered by Burkholder in 1984. It turns out that the Cp, this optimal Cp, in both cases, the Cp, the optimal one is this p star minus 1. Okay, well, this p star, you remember, this was this maximum of p and the harmonic conjugate q. All right. So this, I did not write it here because I did not have place. This p star minus 1 is the best possible. Okay, it cannot be improved. This constant, this inequality is sharp. This is important here. Okay, so this result in a sense can be regarded as a probabilistic version of the Ibanez conjecture. All right. So this f, right? This f, well, plays the role of the function f, okay, and this g plays a role of the Berling-Alphos operator, okay, this bf here. All right. Okay, how did Burkholder prove his sharp estimate? So, well, the idea is very simple. So actually, if you introduce a function v of this form, then observe that this inequality, this thing, is precisely that one, right? If you just take the pth power of both sides, okay, then this is exactly this thing, and put everything on one side, on the left side, right? And this is exactly this. And what Burkholder did, Burkholder constructed a certain special function which has the following properties. First of all, it majorizes this function v, the first thing, and the second thing is when you apply this function, this function u to the sequence f and gn, okay, then the sequence of the corresponding expectations is non-increasing. Okay, so he constructed a function which has the following two properties, and well, if you have such a function, then the claim is evident, right? Because, well, you write this, okay, this expectation, and you just bound it from above by this first, using this first property, this majorization, okay, and then you go to 0. So this is very easy, okay? And what is the special function? The special function is given by the following formula, okay? So this is the so-called Bellman function corresponding to this problem, okay? And this function is given by this beautiful formula, Okay, so here alpha p here in front is just some numerical constant depending on p. All right? And the sharpness was proved with the use of some examples. All right. Actually, let us now turn to some extensions of this result for martingales. Okay, so the previous result concerned martingale transforms. All right. Now, this result holds also for the so-called differentially subordinate martingales. Okay, and what is the differential subordination? Differential subordination is the following condition. All right. So let us start from the beginning. So observe first that now we allow martingales to take values in a Hilbert space. Okay, wherever I write this H, I mean that this is a Hilbert space. Okay, so you see the differential subordination is that if you take the nth difference of G, nth difference of F, then we have the following domination. Okay, of F over G. All right. So this is this differential subordination, that the differences are subordinated. All right. And a similar proof to the one which we have seen previously shows that, well, this sharp estimate is still valued. Okay. Well, of course, perhaps let us also comment. Obviously, this condition is less restrictive than martingale transforms. Okay. Remember, if we in the martingale transform setting, dgn was just dfn multiplied by certain v which was bounded by 1. So this thing is automatic. Okay? So if we have martingale transform, then this condition is evident. Automatic, okay? But of course, on the other hand, this condition is much less restrictive. Okay? It allows a much wider class of processes. Okay? But still, it turns out that this inequality holds. And of course, this p star minus 1 is the best possible, because it was already the best possible in the more restrictive setting. All right. And for our further considerations, it is also convenient to state here the corresponding version for the Haar system. All right. So if we assume that these coefficients ak, bk are dominated in this sense, all right. So for each k, we have this bound, all right, for each k. Okay, then we have this inequality. Okay, this is precisely this version of the theorem applied to this special Haar martingales. All right. Okay, so you see we have here this AK are bounded by BK. Okay, so that was the first extension. Okay, to the so-called differentially subordinated martingales. All right, now we move to continuous time martingales. Okay. Well, as I understand, some of you may not like continuous time martingales, so I will try to not say too much about this, but it will be important for us, so we have to say something. Okay, so let us assume that we have two continuous time martingales, okay, x and y. Okay, the definition is very similar to the one in the discrete time case. Perhaps I will write it on the blackboard here. The definition is that the conditional expectation of xt with respect to some previous sigma field is just the appropriate previous variable. That's the continuous time martingale. Okay? Okay. So, all right. Now one can extend the notion of differential subordination with the use of the so-called square brackets. Okay, every continuous time martingale has its own the so-called square bracket or quadratic variation process. Okay, but if you don't like it, don't worry. Actually, we will not need this. I just wrote it for the sake of completeness. Okay, so just think about examples which appear right now. So first of all, okay, if you have a discrete time martingales, okay, f and g, you can always embed it into continuous time, okay, with the use of these formulas. Okay, and here this floor and floor. Okay, so we can always, if you have discrete time martingales, you can always embedded into continuous time, and then if they were differentially subordinate at the very beginning, then they are also differentially subordinate in the continuous time case. So, okay, of course that's how the things should look like, right? The second example is related to the so-called stochastic integrals, okay? So what we do, we take a Brownian motion W, all right? We take two predictable processes, H and K, which satisfy this condition, this domination, and we take the stochastic integral of H, stochastic integral of K, and we have X and Y. If this condition is satisfied, then this X, then this Y is differentially subordinate to X. Okay, and have a look at the previous slide. There is a discrete time version of this. Have a look. Have a look at this estimate. There is great similarity here. These things are really similar. Look, if you can, in a sense, interpret this HK as a small increment of the Brownian motion, in a sense, all right? And then this thing, this whole sum, is the analog, is the discrete time analog of the stochastic integral of A, of this process A. And here we have the stochastic integral of B, in a sense. All right, and have a look. We assume that AK is dominated by BK, and the same thing appears here. Okay, if we look at this DW and DW as in a Haar system, then we see that this is precisely the previous version, right? Because we have this, that this integrands are appropriately bounded. So this is a version of this previous theorem. Okay, so if you don't like continuous time martingale, you just can think that, well, this thing actually will be important for us. Okay, and you can think that this is some sort of infinitesimal version of this previous result for the Haar system. Okay. All right, and we have a theorem which was proved in '95 by Burkholder and Wang, which says that, well, if y is differentially subordinate to x in this continuous time sense, all right, then this inequality still holds. Okay. And so, of course, still this p star minus 1 is the best possible. Okay, so this is the extension which will be needed. All right, and how the proof goes? Well, it goes along the same lines. So we just use the same function v. All right, and this special function which appeared several slides ago. Okay, so it satisfies these conditions. Okay. Again, of course, it still has this majorization, and well, if one works with some Ito formula or something like that, it satisfies this monotonicity property. Okay, and again, when we have these two properties, this bound follows immediately. Okay, I forgot to write here that this is smaller or equal than 0 at the very beginning. Okay. Can
this also be proven by a sort of discrete approximation from Burkholder's discrete?
Not really. Not really. If you only wanted to prove something for stochastic integrals, then yes, of course. But for general, not really. There are some problems, some technical problems. Okay. So let us briefly review some other related results. Okay. So these were just the LP bounds. So let us now, well, just a collection of some other classical results. So, well, we have the following weak type PP estimates. Okay. So again, we assume that y is differentially subordinate to x. Then we have the following bounds. So we see here we have the weak LP norm of y, which is defined here. Okay, so you see you take just the probability that this psi exceeds lambda, you take the appropriate root here, multiply by lambda and the supreme. It's just the classical Pth norm, weak Pth norm, right? So we see here that this thing, all right, is just the weak type PP estimate for differentially subordinate martingales. Okay, and it turns out that the optimal constant Cp, observed that here is the pth power. All right, so this optimal constant is here 2 over gamma of p plus 1 for p between 1 and 2. This was proved by Burkholder in '84. Okay, and 20 years after that, so it took some time, it turned out that for p larger than 2, it is equal to p to the power p minus 1, everything divided by 2. And here in this case, p larger than 2, the proof is significantly harder. It's really, there are plenty of parameters involved. All right. And of course, I did not write here, but this CP is the best possible. All right. Okay, let us mention about one version which is particularly convenient for application to Fourier multipliers. The only change in comparison to the previous slide is that these are also weak type bounds. Okay, weak type PP bounds. The only thing which is changed is the norming. Okay, we work with some other norm on this weak space. Okay, we take the following norming. All right, here this Q is the harmonic conjugate. Okay, so actually it can be shown, it's a well-known fact, that such an object defines an equivalent norm, okay, for P strictly between 1 and infinity. Okay, and it turns out that for these norms, the optimal constants, okay, are of this form. All right, here again, this power. Okay, so we see for P larger than 2, this thing is not changed, okay, this constant. But it does change for P between 1 and 2. And in particular, it explodes for P approaching to 1. Okay? Okay, and another result which is related is the logarithmic bound. Okay? Because, well, as we have said, as we have seen, these LP bounds hold true for P between 1 and infinity. Okay, so there's a natural question, what happens in the boundary case? For instance, what happens for P equal to 1? So one of the possible answers is that we have the weak type inequality, weak type 1-1 inequality. The other answer can be given by the so-called L log L estimates, right? Zygmunt estimates. It's another very natural object in the study. So that's the statement. So if y is differentially subordinate to x, okay, then we have the following bound. Probably in the first reading, just think about E here as omega. Take as E, take omega, the full probability space. Okay, then what you see, then you see that then here this thing is just the first moment of y. Okay, here you see that we have some L log L function here. Okay, multiplied by k, which needs to be larger than 1. Okay, plus 1 over this 2 times k minus 1. All right? And actually, well, one can show more. One can show this more exact bound with the use of an arbitrary subset of f, of omega. Okay? And of course, well, I did not say this, but again, this constant here is the best possible for each k. All right? This is the logarithmic bound. Okay, and again, well, this list of estimates is much longer. There are plenty of other results, including exponential estimates. This corresponds to the version of this LP bound for p equal infinity. Okay, this thing was the version for p equal 1. One can think about some extensions for p equal infinity. Then one has some exponential bounds. One can also look for some sharp estimates between LP and LQ. Okay, so when these exponents here are different, all right, there are also some restricted weak type estimates and some other results of this form. Okay, all right. Now we move to the point, actually. Namely, we will show what is the version. We have already seen the Martingale version of the Ibanez conjecture. Now let us see the Martingale version of this Gering-Reich inequality. All right? So let us recall. So that was this Gering-Reich inequality. All right? So let us prepare some preliminary analysis of this thing. So as we have said, Berlin-Kalfos operator is the Fourier multiplier with this symbol. Okay? If we apply Plancherel theorem, all right, then we see automatically, immediately, okay, this symbol here is just 1 in absolute value, right? So by Plancherel theorem, you obtain immediately that this B is an isometry. Okay? So if you apply Schwarz inequality, then you get immediately this bound. Okay? So actually, you see, if you want to show this estimate, all that is hard is this bound. Okay? Because for this E, if we integrate over E, that this is trivial. This trivial bound which does not affect here this constant in front of this. All right? So actually, if we prove this type of estimate, all right, then we actually prove also this. Okay, with some different constant, of course. Yeah. With a little bit changed constant, yeah. Multiplied by E or something like that. Yeah. Okay, so let us repeat this inequality. Okay, now come here comes the, well, kind of exotic inequality, right? But well, that was just the explanation why we consider such a strange thing. Okay, so what is going on here? So assume that we have two martingales. Okay, x takes values in the interval 0, 1. Okay, y takes values in the Hilbert space. Okay, and we assume that y is differentially subordinate to x. Okay. Furthermore, we assume that y starts from the origin of the Hilbert space. Okay. And now what happens here? All right, and well, we have the following inequality. Okay, and well, why do we consider this? What is the relation? Because, well, it seems a little bit confusing here. Well, first of all, we remember the role of f, of the function f, is played by the martingale x. Okay, and then the role of y is played by this bf, Berling alphas operator applied to f. Okay, and now look, and here, okay, we apply Berling alphas operator to the indicator function. Okay, so if we take the so the role of the martingale should be played by this indicator function. Okay, and the role of y will be played by b applied to this indicator function. Okay, so if this indicator function is kind of x, so this explains why x takes values in 0, 1, because indicator function takes values in 0, 1. Okay, we expect, so that's why we take here this x, which will play the role of this indicator. We assume that it takes values in 0, 1. Okay, and well, for this b we do not assume anything. We just assume that y is some martingale taking values in some Hilbert space. Okay, and another comment here is, take a look. Here we have this integration with respect to d minus e. Okay, on d minus e. Well, here's the trace of this. Okay, this x will be the indicator function of e. Okay, so if you 1 minus this will be something like complement of e. So this is why this is in this form. In a sense, that's some motivation for considering such a strange inequality. Okay, so in a sense, it's a preparation for this inequality. Okay, and we see here that we have the following constants involved. And of course, for each lambda, the constant is the best possible. It cannot be improved. All right. So let us, well, I could not help resist. Okay, what the proof is really. Okay, so let us see how, well, we have seen what is the Burkholder function for the LP estimates. Okay, so let us see what is the Burkholder function for this Göring-Reich inequality. Okay, for this version, for this exotic inequality. Okay, so all right, so for this function v, we take this expression. All right, and this is clear. The same thing appears here, right? We take a look at this, and we take a look at this, and this is exactly this. Okay, this is what we should take. Okay, this is our v lambda. Okay, and to introduce u lambda, well, first of all, we have to, well, distinguish three special subsets of the following strip. Okay, so these are just some nice subsets of the strip 0, 1 times h. Okay, and here is the Bellman function. Here is the special function. Okay, so for those of you who like Bellman functions, I would only say this is not the optimal Bellman function. This is not the sharp Bellman function. The sharp Bellman function is much more complicated. It involves, if I remember well, it involves 6 regions. If we only consider this best one. Okay, so for the sake of simplicity, okay, I just managed to reduce this number to 3.
But it gives the sharp constant.
Yes, but it does give the sharp constant. Yes. So it is sufficient. Yes. All right, and well, and the rest is as usually. All right, so we check the majorization, we check the initial condition, we check this monotonicity property, and that's it, actually. Okay, so that's how the proof goes. Okay, and well, so finally, let us mention the version which is very similar to this one here. Okay, finally. So remember this exotic inequality. Let me come back. So that was this exotic inequality. Okay, and this inequality implies the following inequality. Okay, and take a look. If we just took this term, all right, and put it on the left side and worked a little bit, and we get this previous bound. Okay, but this is really close to this, because you see, we take for x the indicator. This plays the role of the indicator function of e. Okay, this plays the role of the Berling-Alfors operator applied to this indicator function. As a, one might take the d, the unit disk. Okay, and now that's it exactly, right? Because we have complement of e times the indicator of d. So this is exactly this set here. Okay, and now you see, and how is this thing related to this? Well, have a look here. We have this lambda involved. If you optimize over lambda, you get something in the spirit of this, because you look, the expectation of the indicator function will be just the measure of e. Here we will have the measure of the disk minus e. So these things are really closely related. That's why we consider this strange inequality, because now it leads to a very similar version of this bound below. All right. Okay, so this ends our first part, okay, concerning the martingales. Now we move to the representation, okay, to the deduction of the corresponding bounds for Fourier multipliers, okay, from these martingale bounds. Okay, so now we have this whole probabilistic machinery. Now we apply this whole machinery to obtain some appropriate bounds for Berling-Alfors operator and hopefully for some other wider classes of Fourier multipliers. Okay, so for the sake of convenience, let us recall another classical object, the so-called Riesz transforms on RD. So these are the classical objects in harmonic analysis, just fundamental examples of Calderon-Zygmunt's singular integrals. So, well, the definition is the following. So you see, again, this integral is understood in the Cauchy principal values. Right, here is some multiplicative constant. Okay. So that's the definition of the Riesz transform. Okay, so if we work in RD, then we have D such transforms. All right. These Riesz transforms can be alternatively defined as the Fourier multipliers with the following symbols. All right. So that's the alternative definition. Okay, and well, a remarkable property is the following. Namely, if we are in the planar case, if we are on the plane, right? If the dimension is 2, okay, then the Berling-Alfors operator can be, well, decomposed in the following form, okay, with the use of second-order Riesz transforms. Okay, so you see that in a sense this difference of squares, r1 square minus r2 square, can be understood as a real part of the Berling-Alfors operator, and here this 2 times r1 r2 can be understood as the imaginary part. Okay, so this is just the decomposition, all right? The relation of the Riesz transforms to the Berling-Alfors operator. That will be convenient to us. All right. So now what is the idea? Okay. So now we will describe what is this connection, what is this representation of the Berling-Alfors operator in terms of martingales. All right. So what do we do? Okay. So we start. Okay, so we take the plane, all right, and we take the function defined on this plane, all right. Now, the next step, we take the heat extension to the upper half space, all right. So we take the function on the upper half space, which satisfies the heat equation, all right, and which at the boundary of the half space, it coincides with f. Okay, perhaps I should say that f is sort of regular. Okay, for example, I don't know, just to make sure that everything works fine. For example, that f is from Schwarz class, for instance. Okay, so then we take this heat extension. All right. Okay, so we have this plane and we have a function defined on this plane. Okay, and we raise it to the heat extension to the whole half space. All right, what do we do next? Okay, so we take the Wiener process, the planar Brownian motion, okay, which starts from zero, from complex zero, okay. And now, well, here it comes, all right. Okay, so what do we do? All right, so, well, you take this plane, all right, you take this function f, which is defined on the plane, you extend it to the whole half space using the heat extension. Now, if you take this extension and you start a Brownian motion somewhere here, okay, and you see, and we evolve it in the following form. Okay, so take a look at these brackets. Okay, now forget for a while about this UF. Just look at this. This thing is the planar Brownian motion. I mean, not planar, space-time. Right? This thing is the space-time Brownian motion. Okay, so you see, if we take t equal to 0, okay, it starts from tx. Right? So we have points. Okay, so here is this plane. Here we have the point tx. Okay, and this process starts evolving from this point. Okay, and what happens when t grows, when t increases, then this vertical component goes at the constant speed towards this plane. Right, this first coordinate is deterministic. Okay, and well, the second coordinate, okay, this thing, okay, is just moving somehow, right, on this plane. So it's, you see, so this process is in a sense behaving like this. All right. Okay, so you see what we have here. We have the planar Brownian motion. So this is this, composed with the heat extension. Such a thing is a martingale. Okay, that's Ito formula, and that's nothing special about this. This is a well-known fact from some stochastic analysis, one of the very general facts. Okay, so this is a martingale, and if you use Ito formula, you can write it in the following form. Okay, with the use of the stochastic integral with respect to W. Okay, so if you don't like stochastic integrals, well, don't worry. It's just it, right? Okay, have a look. Perhaps I will say only one thing. Here we have this gradient with respect to x. Okay, it means that we take the gradient with respect to this second variable. Okay, so of course, well, we are on the plane, so this gradient is two-dimensional. So okay, so this thing is a two-dimensional vector. Okay, and okay, we integrate it with respect to the two-dimensional Brownian motion. So everything is okay. All right, now what we do next? That's a specific construction which works fine. All right, now what we do, we transform it, in a sense. Okay, so we had f, we raised it, and we got a martingale. That's the idea. So we have f and a martingale. Okay, now we want to associate a transform of it. Right? We have to proceed this way. Right? Because then we want to use some martingale transform inequalities. All right, so what we do, we take the matrix A, 2 times 2, and we consider, well, a similar stochastic integral, the same thing as here, but the only difference is that you apply a matrix A to this gradient. That's the only change. Okay, so we had this vector, and first we act here by this matrix and then integrate. Okay, and again, this is from the general theory of stochastic integrals. This is again a martingale, and what is important is that when the operator norm of this matrix is bounded by 1, then this thing, this y, right, this transform, is differentially subordinate to x. And you remember, we had this slide, okay, which said that if we have stochastic integral, we have something here, and if this integrand here is bounded by this integrand here, then we have the differential subordination. Okay, that was the second example of the continuous time differential subordination. This with this capital H and capital K. This is precisely this situation. Okay, this thing, the norm of this thing is bounded by the norm of this. So, and we are in the setting of stochastic integrals. So we have the differential subordination. Okay. Unfortunately, that's not the end of the construction, because there is one thing more. But that's it. That's the last step of the construction. So what do we do? Here's again a very strange expression. All right. So actually, what is the idea? So you see, the idea is the following. So you take this plane, all right? You take the function f on this plane, you extend it with the use of heat extension, all right? You associate this martingale x, okay? You transform this martingale x with the use of this matrix A, okay? And now what you do? You take all the trajectories of x of this first martingale. You take all the trajectories of x starting from various points, okay? Okay? From various x's, various small x's, okay? They start from various points, and you take all the trajectories which end at a given point z, okay? So all these possible trajectories which start somewhere, the letter capital T is fixed. This starting time region is fixed, but small x is changing. So all the trajectories which start from various points at level T, okay, and end at z, right? This is this thing, all right? And now what you do, you take this transformed martingale y, or this A star f, all right, and you take the average. So you take all these possible paths. You see what happens on these paths with this martingale y, or this martingale A star f, all right, and you take the average. That's the idea. Okay, that's it. Okay, that's the conditional expectation. That's the average over all the possible paths which end at a given point z. All right. And now, here we go. Okay, if we take the matrix A, which is of this beautiful form, very simple matrix. Okay, then it turns out that if this level t we go to infinity, then we obtain the pointwise limit as this real part of the Berling-Alphus operator. Okay.
Goes to infinity or to 0?
Infinity here. Okay, this starting level t. Okay, there was the starting level t, and you go to infinity with the starting point. Okay. Okay, and similarly, if you take this matrix, you obtain this operator. Okay, so this is almost everywhere with respect to z, of course. All right. So you see, this is very, very close to what we have expected, because, well, we start with the function, we have a martingale. We transform this martingale, and after some conditional expectation only, we obtain the Fourier transform, this real and imaginary part of Berling-Alphus operator. So that's it. You know, we have function and BF, and in a sense we have martingale, and almost it's transformed. Not transformed, but conditional expectation of this transform. But conditional expectation is a contraction. So that's how this should work. Okay. So now the general slide. Well, how to deduce the upper bounds for these special Fourier multipliers. Okay, for this real and imaginary part of
Since you have the two matrices, can't you do like the A1 plus A2, and then, I mean, why do you need to split into two parts? I mean, in the next slide.
Because then this matrix A must be bounded by 1. This operator none. This is why. Yeah. Okay. So what is the general idea? So, well, let us suppose that phi is a convex increasing function. Okay. And well, we'll see how to attack the problem of bounding this thing from above. All right, and this is very simple, because, well, we take the appropriate matrix, okay, which leads to this multiplier, okay, and what you do. So, well, first of all, we do not consider this object, this R1 square minus R2 square, but we consider this S, okay, this conditional expectation. Remember this thing, okay. Okay, so this thing here. All right, so now the first thing, you just apply the definition of this SA. All right, so this is the definition. Okay, but, well, phi is convex, and here we have the conditional expectation. Okay, so, well, using Jensen inequality, okay, or some appropriate form of it, okay, we get from this to here. Okay, and now see what happens. This integrand, this thing under the integral, right? you see, this is just the expectation of phi of some martingale. There's no conditional expectation here anymore. Okay, that's just the martingale which is differentially subordinate to this martingale which is generated by f. So it's exactly what we need, right? So all we do, we just bound it from above using the previously developed martingale inequalities, okay, and then integrate, and that's it. Okay, so let us see how this works. Okay, so so we come to the version of the Ibanez conjecture. Okay, well, unfortunately here this constant 2 is, right, and there's a struggle, okay, how to decrease it. Okay, and there are many works on that, including some recent works of Wahlberg and co-authors. All right, so we'll see how to show this bound, this Ibanez conjecture, unfortunately with this small constant 2 here. Okay, so how do we show this? Okay, so we apply this previous procedure, okay, with the power function. Okay, so again we take the appropriate matrix A, okay, and well, this first step is exactly what we have discussed on the previous slide. Okay, it's exactly this. Okay, that this thing is bounded by this thing. So this is just this inequality. All right, and now see this thing. All right, this integrand, this expectation here. Okay, we use martingale inequalities. This result of Banuelos and Wang from 1995. Right, LP norm of the martingale, which is differentially subordinate, is bounded by the appropriate pth norm of the dominating martingales times this constant. All right. All right, so now, okay, so what we need to check what this xttx is. All right, okay, so what we have here, we have a martingale which starts at level t and moves, and this you see, and here it is stopped at ground zero. Okay, so let us see what it is. Let us come back a little bit. Have a look. If we put here capital T here, all right, then you have here UF0, right? So we are ground zero. Okay, but on the ground zero we have already said that then this extension is just the function f. Okay, the function f at this point. Of course here capital T. Right? So okay, so we come back and we write this down. This is exactly this. So this is equality here. Okay, and that's it. You use Fubini theorem. You just put this expectation outside, and you see what we get here is just the pth norm of f. All right, so we get this bound, right? And we similarly we attack this 2 times R1 times R2. All right, this is treated exactly in the same manner. All right, and what we get? So we get the bound with this beautiful constant for the real part, we get this bound for the imaginary part. So if we add this, combine these two bounds, we get here this 2.
And the bounds, they are sharp. So
yes, exactly. These things, this bound and the similar bound for 2 times R1, R2 are sharp. Yes, these inequalities are the best possible. All right. Okay, so now we turn to the result for the Goering-Reich inequality. Oh, this is the theorem we proved with Rodrigo Banuelos quite recently. So exactly in the same manner, okay? So arguing as previously, okay, we show the following bound. So okay, we take the unit disk D, we take the measurable subset of this disk, okay, and applying this whole procedure, okay, with these heat extensions and all these things and all these things and all these things, and working a little bit, working, we obtain these two bounds, all right? So you see, these are just the appropriate versions of these martingales. If you just replace here this by y, this, okay, and here is 1 minus x, and so on, so on, so on. Okay, this would be just these martingale versions. Okay, so this thing is just the machinery, you know, applied to a different martingale inequality, and you get this. Okay, if you work a little bit, if you added these two things, okay, you would get here the constant 2, as previously. Right? But actually, if you work a little harder, okay, and use the fact that this indicator function is real valued, this is important, yeah, that this is real valued, you can actually, you know, decrease this constant from 2 to square root of 2. All right? And now, if you optimize over lambda, you get the following version of Gering-Reich inequality. Unfortunately, you know, with this constant square root of 2 here. Okay, and you see this constant c here is just e pi over 2. Okay, so that's how it works. Okay, so well, for the remaining 5 minutes, okay, which I have left, okay, so I will mention some results which can be obtained with the use of this methodology, and which yield some results for Fourier multipliers, more general Fourier multipliers. Okay, so well, you remember we used Brownian motion, space-time Brownian motion, okay, and this heat extension. Okay, these things combined yielded the martingale. All right, and then we were transformed and so on and so on. Well, if one works a little bit with some other processes, so if instead of Wiener process, okay, one takes some type of Levy process, okay, some generalization, okay, and well, instead of heat extension, if one considers a related object, corresponding object, the so-called parabolic extension, okay, associated with this Levy process, one may attack these similar things. And what is the outcome? Okay, so well, we obtain a number of interesting estimates, okay, for some strange Fourier multipliers. Okay, so we use other objects, other parameters instead of Brownian motion and so on, and we obtain different Fourier multipliers. Okay, similar results, but for different, wider class of Fourier multipliers. So what do we get? All right, so I will just formulate the results. So assume that mu is a Levy measure on Rd. This is just some measure on Rd with some additional integrability. I will not go into details here. Okay, some simple measure with some special integrability. Okay, and we assume also that mu is another measure on the unit sphere of Rd. Okay, so now we are in the higher dimensional setting. Here we do not assume that d is 2. Okay, so we also allow some higher dimensional things. All right, and now we pick two functions. These are all these things are parameters. Okay, so this mu is parameter, this phi and psi are also parameters. So you see, this is just the phi is the function on Rd, which takes values in the unit disk. Psi is the function on the unit sphere, again with the values in the unit disk. All right? Okay, and you define the symbol corresponding to these 4 parameters. Right, that is a beautiful formula. Okay? Well, that's what we get by this approach. Okay? Okay, such a complicated object. But you know, if you use some special Levy measures, for example, corresponding to some stable processes, you get some sort of interesting symbols here. I'm related to some Martingale multipliers and so on. Okay, and well, once you have the symbol, you define the corresponding multiplier. Okay, this is just the definition of the corresponding multiplier. Okay, just the Fourier transform of TMF is just the Fourier transform of f multiplied by this symbol. Right, that's the associated multiplier. All right, and what do we get? Okay, so Banuelos, Bilaszewski, and Bogdan showed in 2011 that we have the following sharp LP bound for this class of multipliers. Okay, P between 1 and infinity. Sharp, I mean, what I mean by sharp, I mean that, well, if you work a little bit with these things here, you can get the real part and imaginary part of the Berling-Alphus operator. Okay, so this is sharp in a sense that this includes this bound for the Berling-Alphus operator. Okay, so if you choose these parameters appropriately, you get here the real part of the Berling-Alphus operator, the imaginary part of the Berling-Alphus operator, and we know that for these special operators, this estimate is sharp. All right. Okay, so well, one can show with some with these inequalities we have mentioned earlier. Okay, this logarithmic weak type estimate. One can also prove analogous statements for this wider class of Fourier multipliers. Okay, and well, in this recent paper with Federico Banuelos, we managed to show that we also have a quite general, Gering-Reich type inequality, okay, for this more general class of Fourier multipliers, okay, and you see here these multipliers. Let us stress this, that these Fourier multipliers are acting on RD, so the higher dimensional objects. Okay. Okay. All right. So, well, I find that I will not manage. Well, my time is actually up, so I will not manage to say about this sharpness of these estimates. What are the tools? I will only say that, well, this approach exploits the so-called laminates. Okay, these objects are certain special probability measures on matrices. These things occur in the convex integration, in some variational problems. Such objects arise, right? So these are quite natural objects, and well, and there is a recent, very beautiful paper by Boros, Shekelihidi, and Volberg, which gives the which explains the interaction between these laminates, these probability measures, and martingales. A very nice paper, and using this approach, one can show that these bounds, okay, for this real and imaginary parts of Berlin-Alphos operator, okay, are sharp. All right. So well, so I think I will not manage to say anything more. Okay, so that's it. Thank you very much.
Questions?
So this really, the bounds for the Berlin-Alphos really rely on the structure of this second order Riesz transform.
Yes.
I mean, on the martingale structure. What can you do for? I know, can you, with a similar approach, can you just, I don't know, get the norm of the Riesz transforms on LP of the first order?
Yes. Thank you. Very nice question. Yes, you can do this, but then you have to use some martingales which have some additional structure. It turns out you have to use some sort of orthogonal martingales. So they have some additional orthogonality inside. Okay, this is because, well, this first order Riesz transforms, they have some sort of, especially if you look at the one-dimensional case at Hilbert transform, then it's perhaps more apparent. They have some orthogonality. Okay. Okay, I think that I do not want to give any more details. No, okay. Perhaps I will just say that, for instance, if you are in the setting of Hilbert transform, okay, so what you do, you take the harmonic function and you take its harmonic conjugate. Okay, that's what you do. That's the Hilbert transform. Okay, and what if you have harmonic function and its conjugate, then these two functions satisfy Cauchy-Riemann equations. If you take a look at the gradients, these gradients are of the same length and they are orthogonal. And in a sense, this thing is followed by martingale structure. Okay, so you need to develop a similar theory, in a sense, theory.
So in a way, this is like Picarin's original proof.
Yes. Mm-hmm. Yes. With the use of special martingale, they will also be differentially subordinate plus something else.
And can you do just for the Berlin-Alphos? Can you get it's a result of Ivanyan's that the norm of the Berlin-Alphos on as the operator from L infinity to BMO is 3 or something. Right?
Yeah.
Yeah. Can you get that using?
That's another very nice question. Yes, I have tried, but so far I failed. But it's in the sense.
It's very reasonable, but it relies on an ingenious split.
Yes, exactly. Yes, orthogonality properties. Yes, I have worked on that, but still no success. But I strongly believe that something can be said. Perhaps not with the best constant, but something very close.
Any more questions?
I have another question. So back early in the talk, you had an estimate with a k in it, k bigger than 1. I mean,
yes. This L log L.
So the k, why couldn't you optimize with respect to? I mean, if you could, this is.
Yes. That was this k times phi and yes.
And then divided by k.
Yes.
I mean, the k didn't appear in any of the hypotheses of the theorem, right?
K larger than 1 only.
Yeah, that's it.
Yes.
So, but then you can optimize.
Yes. Yes, I can. Yes, of course. I can optimize and get, yes.